set y1 through yn on I. So the proof is that theorem 3.12 applies, which that was the I think that was the initial value problem, okay. And so here I just pick a x naught in the interval. I mean, the theorem I'm using is a non-trivial theorem, which we don't prove in here. It requires techniques of analysis, which are beyond the course. The existence of the solution to the initial value problem is not a trivial result. But anyway, x naught being a point in the interval, then I just make up this set of initial data. Y1 of x naught is 1, and the rest are 0. And then y prime of 2 is 1. And so what I'm doing is I'm just making that the matrix, which we take the determinant of to get the Wronskian, I'm making it be the identity matrix. So so this becomes that, and of course that's equal to 1. It's equal to 1 everywhere. So clearly you can find a linearly independent solution set if you can solve the initial value problem. It automatically follows. So finding that function phi that I talked about earlier today is a corollary of that is that you can find a linearly independent solution set for the constant, not for the constant coefficients, for the continuous coefficient ODE on an interval I. All right. All right, so let's see here. Again, just to get back to what we're doing, we wish to find, first of all, hopefully we can solve the homogeneous problem, and then hopefully we can find a particular solution. You put those together, you solve the whole thing, all right? So I am now going to go and specialize. Let's see here. See, we already covered this last time, operators and calculus, all that. So what comes next is, come on. A wandering Beilou enters. How should we proceed? So we covered the annihilator method last time. That brings us to variation of parameters. So you can stop that and then start it again. Well, that's a good stopping point for a video. So for the uninterested, I can